Section 0.2, I'm going to cover how to write down quantities in physics using significant digits and units. Be sure to watch these videos that I'll link to in our Schoology page. In science, we have a system to keep track of the precision of a measurement. Later in this unit, we're going to discuss precision in more detail. This system is called significant digits, sometimes also called significant figures, which we lovingly refer to as sig figs. To determine the number of significant digits in a measurement, we're going to follow these rules. All non-zero digits, any number from 1 through 9, are always considered to be significant. All the other rules deal with identifying zeros as either being significant or not significant. A zero in the middle of non-zero digits, like the zero in the middle of 503, is significant. Trailing zeros, that is zeros at the end of a number, after the decimal place are significant. Leading zeros, that is zeros to the left of the first non-zero digit, are not considered significant. Trailing zeros, that is zeros after the last non-zero digit, but if there's no decimal place, those zeros are not considered significant. They don't count towards the sig figs. Significant figures are most important during lab experiments. They're extremely useful for telling the reader of your lab report about the precision of the measurements that you're recording. For work on tests or homework, normally you're going to give your answer using the least number of sig figs of any of the information that's given in the problem. In this example, we're going to identify the number of sig figs in several measurements. Here in part A, we have a lone number 3. So clearly this only has one sig fig because it has one non-zero digit. In part B, 3.0 has two sig figs. It has one non-zero digit, the 3, which is significant, and it has a trailing zero after the decimal point, which we also count as significant. In part C, 3.01 has two non-zero digits, the 3 and the 1, and it has a 0 in the middle, all of which are significant. So 3.01 has 3 sig figs. For part D, 0.03 only has one sig fig. The two leading zeros are not significant because they're before the first non-zero digit. In part E, the two leading zeros are not significant. The 3 and the trailing 0 after the decimal point are both significant. So the measurement 0.030 has two sig figs. In part F, 30 only has one sig fig because it has a non-zero digit, the 3, and a trailing 0 with no decimal place, which does not count as being significant. So this only has one sig fig. In part G, 30.0 has 3 sig figs. The 3 counts as significant because it's non-zero. The trailing 0 after the decimal point counts as significant. And then we have a 0 in the middle of two significant digits. So that means all 3 digits are significant. In part H, 300 counts as only one sig fig because it has two trailing zeros that are not significant because there's no decimal point. You will also need to be able to round measurements to the appropriate number of sig figs. Part A asks us to round this number to two sig figs. The second sig fig is in the ones place. So we're going to need to round according to the number in the 10th place, the next digit after the place that we're trying to round to. So we look at the third digit to decide how to round to the nearest ones place. So we should express this value as just 32. In part B, we want to express this measurement to three significant figures. We look at the value of the fourth digit, which in this case is 5. That means we should round the tenths place up, and we should express this as 76.0. In part C, we're asked to express 300 with three significant digits. This is impossible to do with our standard notation. There's no way to note that those zeros are significant. This is where a scientific notation comes in handy. We can express the number as 3.00 times 10 to the second power. This will have two significant digits because the zeros after the decimal place are considered to be significant. Nearly all measurements must be accompanied with a unit. If you were to ask me how much more time it's going to take to get to the end of a long car trip, and I responded with 3, you would likely need me to specify what unit of time accompanied my statement of 3. Did I mean 3 seconds, 3 minutes, 3 hours? With very few exceptions, all measurements in physics require units. Scientists all over the world make use of the standard system called the SI system of measurements. You may know this as the metric system. There are a few versions of the SI system where scientists choose a system for their base units to suit their needs. Physicists use the meter as our base unit for length, kilogram for mass, and second for our unit of time. We're able to combine our base units by multiplying and dividing them to form derived units. An example of a derived unit is our unit for speed, the meter per second. It's also common to abbreviate complicated derived units, such as our unit for force. The unit of force is the kilogram meter per second squared. And because that's such a mouthful, we named that unit we named it the Newton after Isaac Newton. In the metric system, we will make use of prefixes to more easily understand very large or very small numbers. This table shows the 3 prefixes that you'll commonly see in this course. Kilo, represented by a lowercase k, means 1,000. So 1 kilogram is 1,000 grams. A kilometer is 1,000 meters. We also have the prefix centi, which means 1/100th. 1 centimeter is 1/100th of a meter. A cent is 1/100th of a dollar. And the prefix milli means 1/1000th. A millimeter is equal to 1,000th of a meter. Alternatively, we can say that 1 meter is equivalent to 1,000 millimeters. Converting units is a necessary skill for physics students. There are several shortcuts that you may have learned in other classes, but the method that I'm about to show you can work in all situations where you have to convert units. The method is called the factor label method, which you may remember from stoichiometry in chemistry. What you're going to do is multiply the measurement that you want to convert by a factor fraction. A factor fraction is a fraction that always equals 1, and when you multiply by 1, you don't change the identity of your measurement. A fraction that's equal to 1 must have an equivalent numerator and denominator. A fraction with equal numerator and denominator is equal to 1. In this first example, we're going to convert a measurement whose unit has a prefix to a base unit, in this case centimeters to meters. We're going to start out by writing the measurement with its units. It's important to always list the units after the number because that will help you set up your factor fraction in the next step. What we want to do is eliminate units of centimeters from the numerator. So our factor fraction needs to have centimeters in the denominator. And because I know how many centimeters are in a meter, my factor fraction is going to be 1/100 centimeters. The units of centimeters are going to cancel. And to crunch the numbers, I multiply across by all the numerators and divide by any number that's in a denominator. So in this case, 375 centimeters is equivalent to 3.75 meters. In the next example, we're going to convert units where we have a measurement with a prefix to another unit with a different prefix. We're going to start the same way as in the previous example and write our unit, our measurement with units so that we can figure out how to set up our factor fractions. To eliminate kilograms in the numerator, I used a factor fraction with kilograms in the denominator. 1,000 grams over 1 kilogram. Then we can cancel units of kilograms. Now I have to repeat the process to eliminate grams from the numerator because we didn't want to end with grams, we want milligrams. I can multiply by a factor fraction of 1,000 milligrams over 1 gram. I can cancel my units of grams. I can then multiply across by all the numerators and all the numbers in the numerators, giving me 3,200,000 milligrams. Since this is a very large number, we may want to express this number in scientific notation, which is 3.2 times 10 to the 6th milligrams. In our next unit, we're going to start using a homework program, which you might have to express numbers using scientific notation. And in that program, we're going to use the letter E to represent times 10 to the. All units of time are based on two basic units of time. We base it on the year, which is the time that it takes the Earth to orbit around the sun. And this is what determines the cycle of our seasons. A day is the time that it takes the Earth to rotate once on its axis, which determines the cycle of night and day. All other units of time are fractions or multiples of these two time units. An hour is 1/24th of a day, a minute is a 60th of an hour, a second is a 60th of a minute, and they're all fractions of our day. A year divided by a day is not a convenient fraction. Because this fraction is really close to 365 and 1/4, this is why we add a leap year once every 4th year. Actually, not really. It's a really complicated story. Click this hyperlink if you want to find out the full story of when and when not a year is a leap year. The base unit that we're going to use, though, is our second. In this example, I'm going to demonstrate how to convert 4 years into seconds. I start by writing down the measurement to be converted with our units, just as before. I multiply by 365.25 days over 1 year to eliminate years. Then I can multiply by 24 hours over 1 day, eliminating days. Then I multiply by 60 minutes over an hour to eliminate hours. Then I multiply by 60 seconds per minute to eliminate minutes. Finally, I multiply across by all the numerators, giving me my answer, which I will round to the appropriate number of sig figs, 3 sig figs, or 126 million seconds, which I could then write in scientific notation. In the next example, we're going to show you how to convert mixed units, like here where we have hours and minutes. Our first step is to convert one of the units into the other. In this case, I will choose to convert hours into minutes. I can multiply hours by 60 minutes per hour to eliminate hours. I can then multiply across to get 360 minutes. Then I can add the additional 13 minutes to find a total of 373 minutes. I can then convert minutes to seconds by multiplying by 60 seconds over a minute to eliminate minutes, giving me my answer, 22,380 seconds, which I should round to the appropriate number of sig figs, which is 22,000 seconds. In these last examples, I'm going to show you how to convert derived units, units that look like a fraction. To convert 75 kilometers per second to kilometers per hour, all I'm doing is changing the denominator from seconds to hours. When you're converting derived units, it's very, very helpful to write the measurement to be converted like a fraction. That helps you set up your factor fraction. First, I multiply by 60 seconds over 1 minute. That eliminates seconds from the denominator. Then I multiply by 60 minutes per hour. That eliminates minutes from the denominator. And you can notice what I have left over is kilometers in the numerator and hours in the denominator. That's what I was trying to do here. I can multiply across by all the numbers in the numerators, and it gives me my answer, 270,000 kilometers per hour. Here's our last example where we have to convert a derived unit where we have to change both the numerator and the denominator. It doesn't matter which one you change first. Here, I'm going to start by changing the numerator. I'm going to multiply by 1,000 meters over 1 kilometer, and this will eliminate kilometers from the numerator. Next, I'll eliminate hours from the denominator by multiplying by 1 hour over 60 minutes. Finally, I'll multiply by 1 minute over 60 seconds to eliminate minutes from the denominator. I multiply across by all the numbers in the numerator, and then divide by any numbers in the denominator, and this gives me my final answer of 10 meters per second.